Good afternoon, everybody. My name's Jan Gray, and I'm delighted to be here today to give you an update on the GRVI Phalanx Accelerator kit. So the industry is looking to FPGAs to help accelerate important cloud workloads. FPGA accelerators can be massively parallel, customized to an application, beautifully connected directly into the data center. And they're used for applications today like genomics, video transcoding, data analytics, and machine learning. There's lots of cloud FPGA accelerator platforms available and more coming online. But the challenge is to take your living, complex, multi-threaded C++ application and somehow map all those sequential memory accesses into a massively parallel application that uses the full spatial resources of the FPGA. And then with each design change, you essentially have to tape out another complex SoC each day. So I'm working on this GRVI Phalanx Accelerator kit. It's a parallel processor overlay framework. It consists of hundreds of RISC-V cores and a scalable memory system. And the idea is to make it easier for software developers to succeed with building FPGA accelerators. You can take your application, recompile it against some parallel programming model, and then directly run it on the overlay fabric without having to do a bit stream generation. And more of your design iterations are 5-second recompiles rather than 5-hour place and route jobs. It's still implemented in FPGA, so you can still add custom function units and custom standalone accelerators. There's 3 main parts to the system. There's GRVI, which is an FPGA-efficient RISC-V processor. Phalanx, which is a fabric of clusters of these processors and memories and I/O controllers that are all connected together with message passing over a Hoplite 2D torus network on a chip. So GRVI is an austere, simple RISC-V processing element. The design philosophy is that simpler processors give you more processors per die, which lets you express more control and memory parallelism to try and harness those thousands of block RAMs on the device. The GRVI processor implements a subset of RV32I. It's the subset that comes out of the GCC compiler. It doesn't implement CSRs or exceptions. It's optimized as a processing element. It does implement all the multiply instructions, and in a cluster, it implements load reserve store conditional. It's a simple 3-stage pipeline. Some of the resources are shared by pairs of processors in the cluster. And the implementation data path is hand technology mapped and floor planned. It fits in about 300 LUTs, and it runs at 375 megahertz directly coupled to scratchpad memories. You then take 8 of these processors and you collect them together in a cluster. Pairs of processors share small instruction kernel memories. The processors arbitrate for access to a 4-way address bank interleaved 128K shared cluster memory. There's also 4 more memory ports on that cluster memory for tightly coupled memory-based accelerators. You can see on the right a floor plan of one of these clusters of 8 processors. It uses about 3,500 LUTs. And in a 1,000,000 LUT FPGA, you can have hundreds of these. So to compose them together, we use message passing on a simple FPGA-optimized NOC called Hoplite. A message traverses the network as a single flit on unidirectional X and Y rings. At a router, there's a deflecting dimension-ordered routing algorithm, but it also does multicast, optional in-order delivery, and other things. You can see a die plot here of a simple 4x6 torus, where there's 256 wires in each link, so it carries 100 gigabit per second traffic on the links. That uses 3% of a mid-sized FPGA. There's a partitioned global address space across the chip. There's a 40-bit address, which can describe a DRAM address, or a destination plus a local 20-bit address. So when we add a Hoplite router to the cluster and configure it for 300-bit wide messages, which includes the 40-bit address and a 32-byte message, you can then put 32-byte message images in your cluster memory and do a memory mapped I/O, which causes that to be read out and offered to the NOC. or a message for this cluster can be delivered by the NOC and written back into that cluster memory. Since it's 256 bits wide, that takes one cycle. Accelerators can also send and receive messages on the NOC. And we also use the NOC for system housekeeping, like starting and stopping processors and loading the instruction memories. So this is a slide from the third RISC-V workshop, where I had just brought up this 10 by 5 cluster design with 400 processors. Since then, in fact, just about a year ago now, Amazon announced EC2 F1 machine instances with FPGA rent by the hour. And there's two topologies, two configurations of this. The small one has a Xeon processor with 100 gigs of RAM and one FPGA with 4 16 gigabyte DRAM banks. The large configuration has 8 copies of all of that. So 8 FPGAs, 32 DRAM channels, a terabyte of RAM. The FPGAs are connected by a 400 gigabit per second ring and by a PCI Express switch, but these are not exposed in the hardware developer kit yet. The FPGA that Amazon is using is this enormous Vertex UltraScale 9-part. It has 1 million LUTs, 2,000 block RAMs, 1,000 Ultra RAMs, and 7,000 DSP blocks. So quite a lot of SRAM on the device. So last December, I got a development card with this FPGA in it, and I reconfigured a GRVI Phalanx. I relayed it out to use those those Ultra RAMs, and I built a 210 cluster machine which had 1,680 cores and 26 megabytes of SRAM. That was the first, to my knowledge, the first kilocore RISC-V, and at the time, the most 32-bit RISC processors on a chip in any technology. So here's some stats from that design. It ran at 250 megahertz. It runs at 250 megahertz, several hundred billion instructions per second. It has 2.5 terabytes per second of memory bandwidth into those cluster memories. There's about a terabit per second NOC bisection bandwidth, and about 25 milliwatts per core. So trying to get this out into the world and get it connected to system interfaces, I'm working on a GRVI Phalanx software developer kit and a release. So the first task was to bridge those Phalanx network interfaces to standard AXI4 system interfaces, both AXI4 stream and memory mapped. So I've built 2 bridges. One is a message passing bridge. It's a core that allows a host to read and write message buffer images and then send them into the NOC or receive them from the NOC and read them back. The second is an RDMA bridge. It accepts read and write request messages from an agent on the NOC and turns those into DRAM memory transactions, either to store 32 bytes to memory or to read a burst of multiple 32-byte blocks and send them as messages into the NOC. And you can send them anywhere on the NOC. You can do broadcast on the NOC and so on. So I'm targeting this on 2 different hardware platforms. The first is the Pink Z1. It has a Zinc 7020 with 2 ARM cores on it. That hosts about 80 of these GRVI cores, and it's only $65 educational. And the second are these 2 F1 machine instances. So here's a little video of an 88-core GRVI Phalanx plus a frame buffer running on this Zinc. And all the cores are running a just integer matrix multiply. The frame buffer update, all these window console repaintings are messages being sent over the NOC to the frame buffer. And that's the little board there. Okay, great. So back to F1, here's a system layout of a shell, the message buffers bridge, the GRVI Phalanx, 4 of these RDMA bridges. They're directly coupled to 3 DRAM banks, and the 4th one is coupled to a 2-to-1 mux. So the host can read and write one of those DRAM banks as well as the GRVI Phalanx. So that gives you shared memory with the host. And here's some system layouts. Now, unfortunately, in an F1, the shell uses 20-something% of the die, and the DRAM controllers use a lot of the die. So that's a 0-core design. Here's an 884-core design. Each of those clustered regions is one cluster, and there's 3 DRAM controllers. A simpler design with 1 DRAM controller with 1,240 cores, and when you create 8 slots of this on the big instance, that's approximately a 10,000-core single machine instance. Now, as I said, there's no connection. I can't send messages between these FPGAs yet. So currently, I program this with bare metal C++ GCC plus a message passing library, but that's a model only the designer could love. So I'm working on an OpenCL tool stack for this. Now, fortunately, Xilinx and Amazon brought out SDXL for RTL for F1. And I'm going to totally leverage that to get most of the OpenCL work working. So an OpenCL programming model is flat data parallel kernels with an ND range of work items that you're invoking. And the model is you read some stuff from DRAM into your local memory. You have a barrier. You do compute locally, a barrier, and then you write your results back. And I'm going to support that on this model. So on the host, the SDXL stack, I'm just going to completely use that. I'm not going to write any code on the host side. So you'll use standard Xilinx and OpenCL to load your buffers into memory, stage them into the accelerator, launch your kernels, copy the result buffers back. On the Phalanx side, I just have to take the GRVI Phalanx RTL and hook it up to the SDXL shell and those DRAM ports. In this model, I will map an OpenCL workgroup into a cluster and a work item into a processing element. And then when the GRVI Phalanx wakes up, its kernel program and the input data is already in DRAM. It reads it out and it launches it. Now, I don't have OpenCL compilers on this machine, so I'm using a 32-bit core, which doesn't have 64-bit pointers in the compiler. So I have to use a little bit of template class magic and a few other things to get an OpenCL-like kernel compiling programming model on that. So in summary, what I'm trying to do with GRVI Phalanx is to make it easier for regular software developers to succeed with FPGA spatial parallelism. Until this thing ships and is used to build workloads, it's an unproven value proposition. It shows that if you have a frugal design philosophy and you take care with how you use your LUTs, you can build a fairly high-performance system. There's an SDK coming that will have from small configurations up to quite large configurations, and it's all totally enabled by the RISC-V ecosystem, compilers, specs, and libraries, and so on. So thanks very much.